Okay, so this is the last lecture. Okay, so the final exam. Let me write down. Exam will be on August the 3rd. Okay, time will be from 7 p.m. and we go up to 11 p.m. Okay, so I'll give you extra time to write 3 questions. Two at 10 marks each, and one at 15 marks. Okay, and what else? So during the exam, you need to turn on computer camera. Okay, I will just be like what we did in the term test. Okay, there's no recording. Okay, you just see me on the other side of the screen. Then there'll be a quiz 10, and the quiz will be August 29. Not August 29. What am I talking? July 29. Okay, and regarding the term test, let me see. It'll be content from week 8. Let me check week 8 or hold on. Lecture 6. Yeah, week 8. Week 8 until week 13, which is today. Okay, today's lecture will be included in the exam. Okay, so any questions so far? Is this okay for you? Okay, so no question. I'm going to start the lecture. So today we're going to look at the final criteria that we're going to learn, which is known as the simplified Mohs criteria. Then we're going to do a new topic, which is design of beams and deflections using integration method. So this is a very mathematical approach. Okay, so probably you guys have seen it in math before. Okay, so I'm going to start with the simplified Mohs criteria. So this criteria is used for brittle material only. Okay, so some of you might say, why? What did he consider to make sure that this is for brittle material? So one of the thing is what Mohr assume is the ultimate strength in compression is greater than the ultimate strength in tensile. Okay, so stress U is your ultimate strength. Okay, so this is different, right? For ductile material, we focus on yield strength, but for brittle material, we focus on ultimate strength. So Mohs criteria, the simplified Mohs criteria is focused on ultimate strength. And the reason why is because it's brittle material. So why brittle material? This is okay. So I think we have done this before. I'm going to recap. So if we look at brittle material, right? So this is our stress strain curve. So this is for brittle material, it will yield and then it will fracture. Okay, so this is your stress yield. Over here, this is your stress ultimate. So the stress yield is approximately equal to stress ultimate. So this is for brittle material. So just to quickly refresh, so for ductile material, you see this. Okay. So this is your stress ultimate. This is your stress yield. So this is for ductile material. So for ductile material, the stress ultimate is greater than stress yield. Okay, so that is the only reason for Mohs criteria, the stress yield is approximately equal to stress ultimate. So he focused on stress ultimate. Okay, so as we mentioned before, right? I'm going to now draw, not mention before, I'm now going to draw the mapping. Okay, the principal stresses. How did Mohs criteria mapping look like? Okay, so if we were to look at his mapping, right? So on the x-axis is stress A. And then on our y-axis, this is our stress B. Okay. So one of the assumption that, not assumption, one of the condition that Mohs make is the ultimate in compression, the magnitude, okay, the absolute value is so much greater than stress ultimate in tensile. Okay, right. So now, if we were to look into this diagram, so how does Mohs criteria look like? So over here is the ultimate tensile, right? So these are positive. Okay, so they're in tension, right? And then you have negative. Okay, so ultimate compression, and over here is your minus ultimate compression. So just quickly to remind you that stress A and stress B are the principal stresses. So from here we can draw the operating boundary. Okay, we can draw the operating boundary. Oh, sorry, I think this one has to be one up. 3636. Okay, so what I'm sketching now is the operating boundary for Mohs criteria for brittle material. Okay, so it's not the same as you look at for Mrs. or Tresca, okay? Because he made the assumption that the tensile, so at this stage, okay, so all these are tensile, you can see all these are tensile, these are compression, right? So if we look at the equation of this line, okay, so we're going to focus on this line now, okay? We're going to focus on, okay, we're going to derive the equation of this line. Why we derive the equation? So we know whether it's within the operating bracket. Okay, so within the operating bracket means it's inside this boundary that I'm highlighting in yellow. Okay, so if it's inside, the material will not yield, right? If it's outside, the material will yield. Okay, so for this case, it might be worse. It might break. Okay, so because brittle material has no ductility at all. Okay, so if we derive the equation of that line, so we have stress B is equal to, so the slope, so delta y, so is your stress ultimate compression divided by delta y, delta x stress ultimate tension, then you have stress A, okay, and then the y-intercept is minus stress ultimate compression. So we are going to rearrange this. So we have stress B over stress ultimate compression is equal to stress A over stress ultimate tensile minus by stress ultimate compression. Okay. Then you rearrange, or we can get rid of this term over here. So you have stress B over stress ultimate compression, stress A over stress ultimate tensile minus 1. Okay. Then again, rearrange this. You get a criteria where 1 is equal to stress A over stress ultimate tensile minus by stress B over stress ultimate compression. All right. So this is the criteria. This is Mohs criteria. Okay. This is Mohs criteria. Okay. So equation 1 is known as Mohs criteria. Right. And note that stress A and B are principal stresses. And I highlight stresses are vectors. Okay. So they are positive and negative. So now how does this work? Okay, how does this work? Okay, so if we look at, okay, so how does this? So now you know that stress A over stress ultimate tensile minus stress B over stress ultimate compression must be equal to 1. Equal to 1 means it's exactly fallen on this line over here. Okay, so how does this work? Okay, so when, okay, so how does this work? Right. So when stress A